This section will cover the program segmentation control and extended virtual addressing. Segmentation control and extended virtual addressing have been added to the MIPS 32 in Release 3 of the architecture. The MIPS architecture is changing with the times, and today many products are demanding larger memory segments. In previous releases of the architecture, the memory scheme is static in the allocation of memory and the assignment of attributes for the different memory segments. In Release 3, the program segmentation control provides a more flexible memory segment. An OS such as Linux can use program segmentation control to extend kernel and user spaces without losing performance. This is called Extended Virtual Addressing, or EVA. There are also new instructions that facilitate EVA which allow the kernel to access user space as if it were executing as a process in user mode. In addition, it adds the ability of changing both the boot exception vector and the exception vector virtual address and physical addresses. The topics covered in this section are: what are segments and how to program them, how a core is set up for legacy compatibility setting, how segments are set up to use a 3 GB RAM space, boot overlays, which change the boot exception vector physical address, and an example of how Linux uses segmentation control on our Malta evaluation board. Prior to program segmentation control, each segment of the address space was classified as mapped or unmapped. A mapped address is one that is translated through the TLB. KUSEG, KSEG2, and KSEG3 are mapped segments. An unmapped address is one that is not translated through the TLB. KSEG0 and KSEG1 are unmapped segments and provide a 512 megabyte window into the lowest portion of the physical address space, starting at physical address 0. Each segment of the address space is associated with one or more of the 3 processor's operating modes: user, supervisor, or kernel. A segment associated with a particular mode is accessible if the processor is running in that mode or a more privileged mode. The kernel mode is the most privileged mode and has access to the full 4 GB of virtual and physical address space. The user mode is the least privileged mode and has access to the lowest 2 GB of virtual address space when a TLB is used. The thing to take away from this is that up until now each segment was defined with a specific and unchangeable attribute. This mapping is now referred to as legacy mode. It is also the default segment mapping when the core is built for legacy mode. Program segmentation control divides the virtual address map into 6 fixed-size virtual segments whose characteristics are fully programmable. Each segment can be set for mapped or unmapped, kernel, supervisor, or user mode access, and set for any cache attribute. The only characteristic that is fixed is the virtual address range of each segment. Notice that the segment size is different for segments 4 and 5. Segments are programmed using 3 CP0 registers that are used to configure the characteristics of the segments. Each register is divided into 2 16-bit sections. Each section is used to configure a segment. Shown is an expanded segment address table with the CP0 registers and bit fields that correspond to each segment. The size column is the size of the segment, and the address columns are the starting and ending address for each segment. As mentioned in the previous slide, there are 3 CP0 configuration registers. Each of them is split into two 16-bit parts. Each part is used to configure an address segment. This slide shows the configuration fields for a segment in these registers. In the name column, you can see the field name followed by upper or lower bit positions for the two segments in each register. There are 4 fields in each segment. The physical address field, which will map the segment to a physical address when the segment is configured to be unmapped. The access mode, which is the user, kernel, and supervisor mode and cache state. The error condition behavior, which when set changes the segment access to uncached and unmapped. And last, the cache coherency of the segment when it is configured unmapped. The default reset state of these fields depends on the Use Legacy Mode selection at core build time. The settings will be covered in later slides. The next slides will go into detail on these fields. When the segment is unmapped, either by access mode or error condition, it will use the PA field to select the segment of physical memory that corresponds to the virtual segment. Physical addresses can only be set on 512 megabyte boundaries, so that means only the top 3 bits of the 32-bit physical address can be set and the remaining bits will be 0. The table shows the physical addresses that correspond to the PA settings. The AM field contains 3 address mode bits. These are the various combination of address modes a segment can be configured for, mode name, and field encoding. When the EU field is set, the segment becomes unmapped and uncached to the physical address encoded in the PA field. An error condition is one of reset, NMI, or cache error. The C field sets the cache coherency of the segment if its address mode is set to unmapped. The table shows the cache modes with their corresponding bit encodings. As an example of how to configure all segments, let's look at how program segmentation control is used to configure a core to look just like the legacy mode memory map prior to program segmentation control. The slide shows the complete configuration setting for a legacy memory map. The following slides will go through the setting of each segment in detail. The legacy KUSEG segment was accessible in kernel, supervisor, or user mode, with an address range that covers the lowest 2 gigabytes of virtual memory and could be mapped through the TLB to any physical address. When in error state, KUSEG becomes direct mapped and uncached to the lowest 2 gigabytes of physical memory. In the table, segcontrol2, which is CP0, register 5, select 4, is used to program segments CFG4 and CFG5, which correspond to the legacy KUSEG virtual address range. The access mode is 011, or mapped user, supervisor, and kernel, which means it will be accessible through the TLB in all modes for non-error conditions. The error condition field EU is set to 1 to indicate that these segments will become unmapped and uncached when the CPU is in error state. The translation in this state is configured by the PA bits. Segment CFG5 sets PA to 0, causing the mapping of the segment to start at physical address 0. This will cover the first gigabyte of physical memory. Segment CFG4 sets the PA to 010. This will map the segment to the second lowest gigabyte of physical memory. The C field, the cache coherency attribute, does not apply to this segment because it is mapped through the TLB. The legacy KSEG0 was a segment accessible in kernel mode. It had a 512 megabyte virtual address range starting at 8 million hex. It was cacheable and direct mapped to physical address 0. In the table, SegControl1, which is CP0 register 5 select 3, is used to program CFG3. This segment covers the 512 megabyte virtual address range starting at 8 million hex. The access mode is unmapped kernel encoded with 000. The physical address bits are encoded with 000, so this segment will be directly mapped to physical address 0. The cache coherency attribute will be determined by the K0 field in the CP0 config 0 register. More on this later. The error condition field EU is set to 0 to indicate that this section will retain these same characteristics when the CPU is in error state. The legacy KSEG1 was a segment accessible in kernel mode. It had a 512 megabyte virtual address range starting at a million hex. It was uncached and direct mapped to physical address 0. In the table, the SegControl1 register, which is CP0 register 5 select 3, is used to program CFG2. This segment covers the 512 megabyte virtual address range starting at a million hex. The access mode encoding is 000 or unmapped kernel. The PA bits are set to 000, so this segment will directly map to the physical address 0, covering the first 512 megabytes of physical memory. The cache coherency attribute is uncached, so all memory accesses through this segment will go directly to memory. The error condition field EU is set to 0 to indicate that this section will retain the same characteristics when the CPU is in error state. KSEG2 and KSEG3 cover two 512 megabyte virtual address segments starting at C million hex and E million hex respectively. These segments are always mapped, cacheable, and not accessible in user mode. In the table, SegControl0, which is CP0 register 5 select 2, will be used to program these segments. This register controls the configuration for segments CFG1 and CFG0. Segment CFG1 is a 512 megabyte virtual address space starting at C million hex that corresponds to KSEG2. The access mode is encoded 010, setting it to mapped, which means that CFG1 will be accessible through the TLB in supervisor and kernel modes. Segment CFG0 is a 512 megabyte virtual address space starting at E million hex that corresponds to KSEG3. The access mode is encoded to 001 or mapped kernel mode, which means that CFG0 will be accessible through the TLB in kernel mode. Just fixing the segmentation registers does not put the core into legacy compatibility setting. Here is a list of the registers that need to be set for legacy compatibility. Note, all of these registers will be preset to these values if the legacy mode option was selected at core build time. I will go into each of the remaining registers in detail in upcoming slides. There are three fields in the CP0 config 5 register that are used to configure the core for legacy compatibility. The K bit controls the use of the K0 field in the CP0 config register. For non-EVA legacy cores, the K0 field controls the cache coherence attribute of the KSEG0 virtual memory segment. To make an EVA core compatible with legacy software, the CFG3 segment that covers the same range of virtual address as did the KSEG0 segment can have its cacheability controlled by the K0 field. If the K field is set to 0, then the compatibility setting in the K0 bit will override the C field in the CFG3 segment configuration. If the K bit is 1, then the setting of the K0 field will have no effect on the cacheability of the CFG3 segment. The K bit is set by the SI EVA reset pin on reset. If the pin is deasserted, then the reset state is 0 and the cacheability of the KFG3 segment is controlled by the K0 field, and the K bit is writable, which enables the switching from legacy compatibility to EVA setting. If the pin is asserted, the K0 field has no effect. The K field is set to 1 and is read-only, disallowing any change from EVA setting to legacy compatibility setting. In addition to selecting the location of the cache coherency attributes for the KFG3 segment, the config5 K bit also causes the hardware to generate two boot exception vector overlays to be compatible with legacy settings of BFC0 0000 and mirrored at 9FC0 0000. I will go into boot overlays in upcoming slides. The C field controls the cache error exception vector. For non-EVA cores, the cache error exception is forced to virtual address 8,100,000 hex. This is located in the uncached KSEG1 memory segment. To make an EVA core compatible with legacy software, when the CV bit is clear, bits 31 through 29 are forced to a binary 101. This forces the hex address, so the most significant hex digit is A or B, thus forcing the address into CFG2, the segment which corresponds to the old KSEG1 segment. If the CV bit is set, a cache error exception does not force the bits and uses the full 20 bits of the EBase register for the vector. The EV bit is a read-only bit that indicates support for enhanced virtual addressing. The CP0 EBase register has three fields. The exception base field sets bits 12 through 31 of the exception base address. This is defaulted to 800000 hex at reset. The WG bit controls the writing of bits 31 through 39 of the exception base address. For non-EVA cores, bits 31 through 30 of the exception base address are not writable and are set to a binary 10. This forces the exception to a virtual address in the legacy KSEG0 and KSEG1 segments. To make an EVA core compatible with legacy software, on reset, bits 31 and 30 are set to a binary 10, and these bits are unchanged on writes to the EBase when the WG field is equal to 1. This forces the exception base into the CFG2 and CFG3 segments, which correspond to the old KSEG0 and KSEG1 legacy segments. If WG equals 1 in the written value, then the bits 31 and 30 are overwritten. The CPU num field is the CPU number of the processor executing the read of this register. All EVA cores have a new feature called Boot Exception Vector Overlay. This overlay maps the virtual boot exception vector to a physical address overlaying any segment configuration. This is done to add more flexibility because both the virtual and physical address of the boot exception vector can be changed and are no longer limited to BFC000 and physical address 1FC0000. This is called the boot exception overlay because it overlays part of the configuration for the memory segment it is in. The BEV overlay is always present whether or not the core is in EVA setting. The BEV overlay is predefined at core build time so that core 0 will always use the overlay mapping that was built into the core. Core 0 can make changes in the BEV overlay for the other cores before core 0 powers up the other cores. That way they can run different boot code. The next two GCR registers are used to configure the BEV overlay. The boot exception base field in the core local reset exception base register controls where the CPU will fetch the first instruction from on a cold reset. For a legacy setting, the start of the boot exception vectors is located at virtual address of BFC00000, set as the default state for the GCR core local reset exception base register. If you want a core to cold boot from a different address, not legacy setting, then this register can be configured at IP configuration time for a different address. If you wanted to have CPUs that use different boot code, you can access this register through the core other group from another CPU and set the boot address for this CPU. This register also depends on the setting of the next register, the core local reset exception extended base register. Bits 12 through 28 will also be used for bits 12 through 28 of the physical address for the boot exception vector. To see what the BEV overlay is and to change the BEV overlay, there is a global configuration register called the core local reset exception extended base register. This register is an extension to the core local reset exception base register. The value is used for placing the boot exception vectors within the physical address map during core boot up time. This is a per core register, so it is in the core local section of the global configuration registers. The initial value of EVA reset is set at IP configuration time. The EVA reset bit controls the SI EVA reset pin. This pin is then driven by the CM to the core. If the EVA reset bit is set to 0, then the SI EVA reset pin is deasserted, which drives the K bit to 0. In this case, the K0 field in the CP0 config register will control the CCA of CFG3, and the CP0 segmentation control registers will reflect legacy mappings for KUSEG, KSEG0, KSEG1, and KSEG2 and 3. In other words, it will map and behave just like a legacy core. If the EVA reset bit is set, then SI EVA reset pin will be asserted at boot time, and the K bit will be set and unchangeable. This means that the state of the core is not legacy compatible and can never be set for legacy compatibility. The K0 bit in the CP0 config register is disabled, and the CCA of CFG3 is controlled by the settings in the segmentation register. The CP0 segmentation control registers will reflect the EVA mapping for a 3 GB RAM region. The details of this mapping will be shown in a later slide. The legacy use exception base bit will force the boot exception vector address that is in the core local boot exception base register to be located in segments CFG2 and CFG3, which correspond to the legacy KSEG0 and KSEG1 regions, by overriding bits 30 through 31 of the boot exception vector address and forcing them to be A10. Here is a summary chart of the effects of setting the EVA reset bit. Continuing with the reset exception extended base register, the BEV exception base mask determines the size of the overlay region from 1 MB to 256 MB in powers of 2. The initial value is set at core build time. The size also determines where the overlay starts. The overlay will start on a boundary that corresponds to the size of the overlay. Here is a table that shows the mask bit encodings and the associated overlay size. For example, if the physical address of the boot exception vector were to be BFC0000 and the base mask was set to 16 MB, then the start of the overlay region would be the 16 MB boundary of BF00000 and end at BFFFFFF. The physical base address is set using the BEV exception base PA. The boot exception vector base physical address is a 7-bit field, but the current cores only use the first 3 bits. The remaining lower bits, 28 through 0, of the address come from the core local reset base register. Having control of the top 3 bits allows the physical address of the boot exception vector to be placed in any segment. This address and the boot exception base mask then determine where the overlay will be in memory, as shown in the previous slide. The present bit is always set if this register is present. It is a read-only bit. The boot exception vector overlay is always present. For a core that boots with legacy settings, the core local reset exception base register and the core local reset exception extended base register are present at core build time with default values that match legacy virtual addresses. Here are the legacy settings for the BEV overlay of 1 MB. The legacy virtual address base address is set in the core local reset exception base register. The EVA reset bit is 0 to indicate that this is a legacy setting boot. The legacy use exception base is set to indicate that the complete address of the core local reset exception base register will be used for the virtual address. The BEV exception base mask is set to 0 to indicate an overlay size of 1 MB, and the BEV exception base PA is set to 0 so that the top 3 bits of the address are cleared. When combined with the bits 0 through 28 of the BEV set in the core local reset exception base register, this sets the physical address to 1FC00000. Note that the physical address can be set to another address and the core still be considered in legacy base setting because it still uses the virtual address of BFC00000. Here is a table of the segment control registers combined with the boot exception vector overlay when EVA reset equals 0, putting the core into legacy compatibility settings as discussed in the previous slide. I'll go through what you would see in the registers if the core is set up at build time to boot in EVA mode with a boot exception vector at BFC00000 both for the virtual and physical address instead of the physical address of 1FC00000 with a 16 megabyte overlay size. The boot exception base field in the core local reset exception base register will be set to BFC00000, which sets the virtual address of the boot exception vector. The core local reset exception base extended register will be set to 87F0000B. Here's how that value is arrived at. The EVA reset bit will be set indicating that the address configured by the core local reset exception extended base and the core local reset exception base register will be used for the virtual and physical address of the boot exception vector. The legacy use exception base will be cleared, so bits 31 and 30 will remain as they are in the core local reset exception base register. The BV exception base mask bits 27 through 20 are set to 0F. This sets the size of the base address to the 16 megabyte range. The BEV exception base PA bits 7 through 1 are set to 5, combining these with bits 28 through 12 of the core local reset exception base register sets the physical address to BFC00000. Here is the map again showing the overlay region in relationship to the boot exception vector. The K bit in the CP0 config 5 register would also be set, which disables the K0 field in the CP0 config 0 register, so it will no longer control the cache attributes of the CFG3 region. This table shows an example of a 2 GB physical RAM memory map when the boot exception vector overlay moves to the physical address set up in the previous slide. If the system is set up with an overlay that changes the physical address of the boot exception vector to BFC00000, and if the I/O register placement was also placed at an address above the first 2 gigabytes, then there is no longer a hole preventing a contiguous block of RAM memory. Note the default value of the global configuration base register is set to 1FBF8000. This will also need to be changed to an address outside of the RAM memory space. Also, the I/O registers and the GCRs can be located within the BEV overlay region, which is preferred because it is guaranteed to be unmapped and uncached. Next, I'll cover how to set up the segmentation registers to expand the kernel and user mapped virtual addresses and physical address range to 3 gigabytes. The main purpose of the program segmentation control is to expand the virtual and physical address availability in user mode and to expand the unmapped virtual and physical address space in kernel mode. Also, to be able to overlap the two and make it easier for the OS kernel to access the user address space. This table shows just that. It configures a virtual memory from 0 to BFFF as the first 3 gigabytes of virtual memory accessible in user and supervisor mode as a mapped region. For the same virtual range, it sets up kernel mode access as unmapped and directly translated to the lower 3 gigabytes of physical memory. It does this by using segments CFG2 through CFG5. The top 2 virtual memory segments CFG0 and 1 are set up as mapped kernel mode only. In error mode, the lower 3 gigabytes of virtual address become directly translated and uncached. The MIPS32 R3 architecture includes load and store instructions that allow the kernel to access user space as if it were the process whose ASID is currently set in the CP0 entry high register. The E instructions function exactly in the same fashion as their counterparts, except that the address translation is performed using the user mode virtual address space mapping in the TLB. The memory segment must be configured to use the mapped user, supervisor, and unmapped kernel access mode, unmapped user, supervisor, and kernel, or mapped user or supervisor and kernel access modes. The names for these instructions just have an E appended to the normal non-EVA load and store instruction name. All of these instructions have the same meaning as their non-EVA counterparts, except that they are kernel mode instructions that use the user mode translation of the address for the load or store based on the current entry high ASID value. The next slides show the use of segmentation and EVA when used with Linux. This example uses a MIPS Malta evaluation board for a test platform. The evaluation board is limited to a maximum addressable memory of 1.75 gigabytes due to a limitation of the memory controller on the board. The first RAM region is 256 megabytes, starting at physical 0. The second RAM region occupies the region between 2 and 8 million hex, a 1.5 gigabyte region. There is an I/O hole between the 2 RAM memory regions used for the boot flash, I/O device drivers, and memory map GCR registers. Since the I/O address used is the same as the legacy cores, no device drivers needed to change. The next slides show the value programmed into the segmentation registers and how they pertain to different processor modes. This first memory map is of the Linux kernel when running in kernel mode. Segments CFG3 and CFG2 correspond to the old KSEG0 and KSEG1 regions and directly map to the lower 512 megabytes of physical address. which encompasses the low 256 megabyte RAM area and I/O space. Segments CFG5 and CFG4 correspond to the old KUSEG region and are directly mapped to the lower 2 gigabytes of physical address space, encompassing the 2 RAM memory blocks and the I/O space. Segments CFG1 and CFG0 correspond to the old KSEG2 and KSEG3 regions and are both mapped through the TLB. This is the memory map for the Linux kernel running in user mode. Segments CFG2, CFG3, CFG4, and CFG5 are all mapped through the TLB, expanding the user virtual memory to 3 gigabytes. Segments CFG0 and CFG1 are not accessible. Here is the map for error conditions: reset, NMI, or cache errors. Segments CFG 0, 1, 2, and 3 correspond to the old KSEG 3, 2, 1, and 0 respectively, and all direct mapped to the lower 512 megabytes of physical address, including the low 256 megabyte of RAM and I/O space. Segment CFG5 is directly mapped to the lower 1 gigabyte of physical address space, which includes 3/4 of a gigabyte of RAM divided into 2 parts with the I/O space in between. Segment CFG4 is directly mapped to 1 gigabyte of physical RAM starting at 2 gigabytes. For the Linux kernel to use the extra memory, the add memory region function is used to register the memory. See the arch MIPS Malta memory.c to see how this is done for the Malta board. Since the mappings and the cache attributes remain the same, existing device drivers and root file system can be used without any modification. The changes to the Linux kernel can be classified into the following. Files marked in gray are for generic CPU detection, FPU initialization, and instruction emulation. Files marked in purple contain functions that need to copy to user space or from kernel space. These functions have been changed to use the EVA load store instructions. The reason for this is that there is no KUSEG segment anymore, and segmentation control registers are not programmed to be kernel mapped. In the old legacy core, when data was copied from address space in user mode to an address space in kernel mode, LW and SW instructions could be used because both KUSEG and USEG were mapped. Files marked in green have been changed to use the new TLB instructions to invalidate TLB entries. Files marked in white are needed for the Malta board to configure EVA and use the larger RAM memory. This is platform specific. The key functions for these files set up the memory descriptor for Linux to register the appropriate memory that has been detected, register the memory with the add memory region function, and set up segmentation control registers. Another thing that has been changed in the Linux kernel for the Malta board is the code that accesses the I/O registers. The macro checkseg1 adder in adderspace.h has been changed depending on the settings in the Malta specific spaces.h include file. This macro should be used when a device driver needs access to an I/O control register via an uncached address. The macro supports a 3 gigabyte RAM space. It is needed because the kernel normally used the KSEG3 region as uncached for this purpose, and when the core is programmed for 3 gigabytes of RAM, the corresponding CFG0 region is configured to use as a DMA zone. It is recommended that you use a similar approach when you need to support 3 gigabytes of RAM. When the kernel is configured to support 3 gigabytes of memory, it will use the CFG0 segment as a DMA zone. This segment will be configured by the kernel as unmapped and uncached, configured into the lower area in physical memory. The kernel will configure the CFG2 segment for I/O coherence when there is less than 3 gigabytes of RAM memory, the same as it configures the CFG0 segment when there is 3 gigabytes of RAM memory or more. In all cases, the CFG1 segment is configured by the kernel as a map segment used for vmalloc and loading kernel modules. This is the end of the segmentation and EVA section of the course.